Good morning, professors and judges. I'm Chan Si-hin from Pushing Middle School. Today I'm going to present on my topic of containing geometric objects with random inscribed triangles in a circle. To start with, our paper is inspired from a problem in the Putnam competition year 1992, problem A6. The problem asks if we randomly choose 4 points on the surface of the sphere, what is the probability that the tetrahedron will contain the center of the sphere? The answer is 1/8. And so we ask if this problem is also valid for the two-dimensional case. And now we'll state our 2D version of the problem. We choose 3 points instead of 4 points, and on the circumference instead of the surface of the circle. Here, the triangle ABC contains the center O, while in this one it does not. And so, by some observations, we know that C lies in the arc PQ if and only if the triangle ABC contains the center O. And therefore, we define the arc PQ to be the feasible region for C, and we'll integrate over the central angle POQ to find out that the answer is 1/4. And we ask, what if the triangle contains other geometric objects? For example, an arbitrary point, an arbitrary segment through center, or a concentric circle. And so our paper will be divided into these 3 generalizations, and we'll also propose an open problem at the end. We'll first move on to the first generalization, and which considers an arbitrary point. Given fixed D with a fixed distance to the center, fix arbitrary point A and B, and we can find some C such that the triangle ABC contains the point D. And therefore, by similar arguments, when C is on arc PQ, triangle ABC will contain D. And by previous results, we know that when D equals to 0, the probability is 1/4 because this point O and D are the same. And when D equals to 1, the probability is obviously 0. And therefore, we ask, how does the probability change when D ranges from 0 to 1? And therefore, we have our second version of the problem, which asks us to find a probability function PD to describe the probability. Some first guesses are, is the function a linear function, a quadratic function, or a square root function? But the answer turns out to be a graph as shown. Notice that this is not the square root function, but instead this function involves a special function called the spans function. And we'll explain why in the following section. So firstly, we'll find the central angle of the feasible arc PQ, which is the blue angle here. And this is a lemma that we use frequently to find the central angle. This is proved using sine law and cosine law. And we're now going to state our main results. This is the probability in its integral form. And now that we see how frequent the function with the arcsine function comes up, it's more convenient to give it a definition, as shown here. And therefore, the probability function can be transformed into this form. And now we're ready to give the closed form of the probability, which is as here. The Li2 function is the spans function, defined as the infinite sum of the powers of x divided by n squared. And we'll now cover the proof of this theorem. Firstly, this is an integral in the probability function, and we can transform it into a single variable integration through some symmetry, substitution, etc. And then from this single variable integration, we'll transform it back into double integration because the integration of u times the function f is hard to find. Notice that the order of the integration is changed as well. And then we can make this integral into an infinite series by through these steps, which is by considering the logarithmic form of f and the Maclaurin series of the logarithmic form, which is convergent because of the reason that's shown. And finally, we'll pull the summation out, and by some simplifications, we get the desired results. This shows the whole flow of our proof. This is step 1, step 2, step 3, step 4, and step 5. In this session, we covered the probability considering an arbitrary point, which is shown here. We found a beautiful closed form, and this is a new relationship between geometry, probability, and the spans function. And here shows the graph of PD, and we'll illustrate our results using an example. By using this identity of the spans function, we can get an exact value of the probability at 1/√2, which is this. We'll now move on to the second generalization, which considers an arbitrary line segment D1, D2 that passes through the origin. So firstly, define a similar probability function P2, and then we'll consider 3 cases in this section. The first one is when the endpoints of the line segment are the center and an arbitrary point, and the other 2 cases are when the endpoints are arbitrary 2 points and the line segment passes through the origin. Due to the time limit, we'll only cover the first 2 cases. Firstly, if we want triangle ABC to contain the center O, we need C to be on the arc SP. And if we want the triangle ABC to contain the point D, we need point C to be on the arc QR. And therefore, when C lies on the intersection of the 2 arcs, which is QP here, triangle will contain the line segment OD. But notice that when A and B are too close, the two arcs may not intersect, and therefore we want to find the condition for AB such that the arc actually intersect, which is here. This is an inequality showing the condition of A and B, and this is proved by considering the boundary case, which is when the two arcs intersect at only one point, and it is easily proved by angle chasing. And finally, this is the integral form of the probability function. Notice that the lower limits of the inner integral and the integrand are different from before. Notice that in previous part, we are integrating over this blue triangle, but in this, with the newly added condition, we are integrating over this blue region instead. And therefore, by referring to the graph, we get this result. And by simplifying the above integral, which is easy because notice that the function f is independent to a, and we get the single variable integral. And the expressions that prevented us from finding a closed form is the square of the function and the function times b. And we'll illustrate our results using an example as well. By using trapezoidal rule, we get when d equals to 0.5, we get this probability. And actually, after submitting the paper, we found the closed form of the probability as shown here. Notice that the Spence function comes out again, which is very beautiful. And now we'll move on to the second case, which is an arbitrary segment through the origin. By similar arguments, we get a bound for AB, and we get the integral form of the probability as well. And this integral is integrated over this region R. And this is a plot of the integrand. And notice that we are integrating the region behind the green curve. And so our flow of this section will be firstly prove that T is strictly monotone in two directions, and then we will show A and B in the green curve is before have a one-to-one correspondence. And finally, we'll use multi-color integration in our own algorithm. And my steps is in the paper, but I'll now illustrate my results with example. When the values of D are this particular set, we get this probability. And now we'll move on to the third generalization, which considers an arbitrary concentric circle, which is the red circle here. And define similarly the probability function PR. And by Euler's inequality concerning the circumradius and inradius, we get this simple bound, which is when R is larger than 1/2, the probability is 0. And we'll consider two boundary cases this time. In the left figure, when A and B are closer, then there are no triangle ABC to contain the circle. While in this, the right figure, when A and B are wider, then there are also no triangle to contain the circle. And we get this bound, which has a lower bound and an upper bound. And we'll also get this integral form by referring to the graph. Notice that the region that we are integrating is actually a trapezium, which is intuitively easier to integrate. And we get this closed form of PR. And here's the plot of PR, and we ask, is there any application of this problem? Firstly, we'll consider other geometric objects, such as a regular n-gon centered at O. But let Pn be the probability of containing a regular n-gon. And using the above results, we get this bound, which is the circumcircle and the in-circle of the n-gon. And finally, we'll state our open problem, in which ask when the probability when the circle is moved d units away. And we want to find a similar probability function that depends on D and R. But unfortunately, this problem cannot be solved because of the complexity of the configurations, and the central angle POQ is also hard to find. And in conclusion, in session 1 and session 3, we covered an arbitrary point and a concentric circle in which we find a closed form. And for the generalization 2, which is an arbitrary line segment that passes through the origin, both of the cases we can numerically approximate the integral. But in particular, when the line segment have origin as an endpoint, we find a closed form after submitting the paper. But for a line segment passing through origin, which is arbitrary, the closed form is still a mystery to us. Thank you.